Okay, first of all, please support my channel and subscribe on my channel, and please do not watch this video by downloading and just watch online. In the continuation of Spline, we have to find cubic spline. So let me define the problem. Let x0 to xn and y0 to yn be n plus 1 nodal points. Okay, now we want to find cubic spline S of x from a interval a and b to r, such that S at each xi be equal to yi for I equal to 0 to n. Okay, to this end we have to find some polynomial, some cubic polynomial like pix. So let me write to this end we have to find pi of x, where pi of x is a cubic polynomial such that this polynomial have three properties. Pi at xi should be equal to pi minus 1 at xi. Pi minus 1 at xi from left should be equal pi at xi from right, and it's p prime, and p double prime I minus 1 at xi from left is p double prime pi at xi from right for I equal to 0, 1, 2, and so on to n. Okay, now if we consider each pi of x, if pi of x be, for example, let me write it like this: a 0, or let me write a I0 x3, or let me write in other form, let ai3 x cubed plus ai2 x squared plus ai1 x plus ai0. Okay, each pi of x has a form like this. Okay, so or then we have 1, 2, 3, and 4. We have 4 unknown coefficient. Okay, but if you have a look at here, okay, if you have a look at here, so and because this polynomial should be compute for I equal to 0 to n, n, from 1 to n, okay, 1 to n. So totally we have 4n unknown, okay, so totally we have 4n unknowns. But we have just 3 times n minus 1 constraint in let me call it number 1, okay, constraint in 1, no, let me fix it, let me call it 2 and call it 1. Now it's okay. We have 3 times n minus 1 conditions here and n plus 1 condition here. Okay, so we have 3n minus 1 constraint in n and n plus 1 unknown, n plus 1 constraint in 2. Yes. So totally we have 3n minus 3 plus n plus 1. So it be 4n minus 2. 4n minus 2 constraint. This is okay. But the system has 4n unknowns, and if we want to find a unique solution for the system, we need 2 more constraints. Okay, now we can use one of 3 following conditions. We can employ one of 3 following. Number 1, or A. The first one will be S double prime at A should be equal to S double prime at 0. Okay, this is one, and in fact both of these should be equal to 0. So the first one give us the first constraint, and the second one give the second constraint. So, or we can use this one. In fact, S is periodic, or FB periodic. FSB periodic. What does it mean? It means that S, the kth derivative of S at A, should be the kth derivative of S at B for j equal to 0, for k, not j, we don't have any j here, for k equal to 0, 1, and 2. This is the second condition that we can employ. And the third one is s prime of a and s prime of b are equal to some special values. Okay, one of these two conditions can be employed. Okay, if we add these two constraints to for n minus 2 constraint that appears from conditions number 1 and number 2, we will have a system of equation with 4n plus 1 equation and n plus 1 unknown, and we can find the solution for the system. And in fact, the spline have been computed. Okay. Now we want to show that under each one of these three conditions, there is a unique spline. In fact, a unique cubic spline. The proof of this concept is not very short, and we have to do lots of computation that I have to do it. But let me in fact start here, and I do some computations, and after 10 or 15 next minutes I postpone the continuation of the proof for the next lecture, because if I start and I want to finish the proof, it will need lots of time. So let me start here. Let S equal to S of x be a cubic spline correspond to the partition A equal to x0 less equal x1 less x2 and to xn equal to b. So S of xi should be equal to y, I for I equal to 0 to n. Okay? Now, consider the length of this j plus 1th subinterval. Now, set hj plus 1 be equal to xj plus 1 minus xj for j equal to 0, 1 to n minus 1. In fact, this hj is length of j plus 1th interval. Okay? and let mj be equal to s double prime at xj for j equal to 0, 1, 2, n. Okay, we can in fact assume something like this. Now, we know that s of x over each interval xj and xj plus 1 is a polynomial of degree 3. Okay, so s double prime of x on xj and xj plus 1 is a linear function. But since look at here, we assumed that mj equal to s double prime xj. Okay, so I can rewrite it here. S double prime at xj equal to mj, and if you compute s double prime xj plus 1, so in fact we can put it equal to mj plus 1, right? We can consider it like this. So if you integrate over in fact x, okay, so in fact this implies that not integrate, but from these two conditions you can find that s double prime of x should be equal to mj times xj plus 1 minus x over xj plus 1 minus xj plus mj plus 1 x minus xj over xj plus 1 minus xj, right? And also we can write s double prime of x if we consider the above notation here for hj plus 1 and mj. Okay, you can write here instead of xj plus 1 minus xj, you can write hj, so we have mj, this is j, mj over hj plus 1 times xj plus 1 minus x plus mj plus 1 over hj plus 1 times x minus xj. Okay, these relations are true for all x between xj and xj plus 1. And you can put also an equal here. Now, take integral from this function, okay, over the interval xj and xj plus 1. So let me write, take integral from s double prime of x over xj plus 1. What we get? The integral from s double prime is s prime of x. So I can write s prime of x be equal to, here we know that the integrate of this one is minus 1 over 2 mj times over hj plus 1 times xj plus 1 minus x squared. So I will get minus mj over 2hj plus 1 times xj plus 1 minus x squared. And from the second one, something same will happen. So I will get mj plus 1 here over 2hj plus 1 over 2hj plus 1 times x minus xj squared plus, in fact, a constant aj also appear at the end of the function. Okay? And we integrate again. درسته؟ Okay? Integrate again. We will get s of x, here it's not s, it will be x, is equal to, here again, if we integrate from these terms, we will get mj over 6hj plus 1 times xj plus 1 minus x cube plus mj plus 1 over 2hj plus 1 times x minus xj cube plus aj times x minus xj plus bj. This is true for all x in the interval xj and xj plus 1. Now we enforce some conditions on s of x. Okay, so now enforce s at xj should be yj and s at xj plus 1 should be yj plus 1 to the latest equality to get, okay, what we get? We get here, in fact here, s of xj. If you put xj, this one will be 0, this one will be 0, okay? So it just remain this one, xj plus 1 minus xj. It will be hj plus 1 cube. In fact, the hj plus 1 cancel with 1 hj plus 1, and it remains mj hj plus 1 squared. So it will be mj hj plus 1 squared over 6 plus bj will be equal yj. Okay, and if we apply this one, this term will be 0, and here mj plus 1 times hj plus 1 squared plus aj hj plus bj will remain. So I can write mj plus 1 hj plus 1 squared over 6 plus aj hj plus 1 plus bj equal to yj plus 1. Right? From these two equations, we can, in fact, find aj and bj. Look, mj plus 1, hj plus 1 are, in fact, noun, and we can find aj and bj as these two values. aj will be equal to yj plus 1 minus yj over hj plus 1 plus hj plus 1 times mj minus mj plus 1, okay, over 6, and also bj will be equal to yj minus mj hj plus 1 squared over 6. Okay, we will get from this system, if you solve this system for aj and bj, you can find these two equations, right? We will have something like this. Okay. But note that okay, let me stop the proof of the theorem here and postpone the continuation of the proof for the next lecture, because we need some more times, and if I start here, the length of the video will be very much and it's not good. So just follow my channel, subscribe my channel, and watch online please, and wait for the next lectures. Thank you.